All right, welcome back everyone. So in the last class, what we saw is we tried to basically formulate the net radiation exchange between two black bodies whose areas were AI and AJ. And of course, AI and AJ were black bodies. And we said that the net radiation exchange between these two bodies, which were represented by QIJ, was basically equal to uh, AIFIJ times EBI minus EBJ, where we have used the fact that the reciprocity relation of the view factors uh, comes into place, and of course, these AI and AJs are black bodies typically. Okay. And then what we said is that we can equivalently represent this net radiation exchange by using a radiation network where the nodes were given by the emissive powers of the respective bodies, which were EBI and EBJ. And the resistance was basically uh, nothing but the space resistance, which we said, and it came out to be equal to 1 by AI times Fij, where we call this resistance as the space resistance. Okay, so equivalently, we can write the net radiation exchange between the two bodies as the difference between the two voltages. For in this case, it came out to be the emissive powers. In context to conduction, it was the temperatures. But here, since we know that the emissive power is proportional to 4 power of its temperature, so we cannot write the nodes as just the temperature values, but rather we need to consider the emissive powers. So it basically then came out to be EBI minus EBJ divided by the resistance, which for the case of a black body, it came out as a space resistance. Okay, we'll call it as RTH of space, and this RTH of space is equivalent to 1 by AI times Fij. Okay, and you can also write this as or 1 by AJ times Fji from the view factor reciprocity rule. Okay, so this is something that we saw it in the last class. So now what we'll do is we will increase our uh, investigation to real bodies. And although I'll not prove, you can rigorously prove this, but I guess the proof has been discussed in the lecture videos. So I will not discuss the proof, but for real bodies, now let's say AI and AJs are real surfaces, meaning that their individual emissivities, which is epsilon I and epsilon j, these are less than 1, which is the case for a real surface. So if you basically now have a real surface, your radiation network now need to incorporate two more extra resistance, which we call it as the surface resistances of real bodies. So now the emissive the radiation network which we draw, for instance, if A is the radiation network for black body, so had now been these were real bodies, so we will now need to incorporate two extra resistance. So the space resistance will still be there, which is equal to 1 by AI times Fij. And now in between the space resistances, instead of having the emissive power nodes, we will basically have the radiosity nodes represented by Ji and Jj, basically. Okay. And between the radiosity nodes, because of the fact that the emissivities are not equal to 1, we will have two extra resistances. For instance, between the radiosity nodes and the emissive power nodes of body I, we'll have a resistance known as 1 minus epsilon I by AI epsilon I. And similarly, we'll also have the other resistance as 1 minus epsilon J by AI epsilon J, where these resistances, this 1 minus epsilon I by AI epsilon I, or this 1 minus epsilon j by aj, sorry, this will be aj, so this is aj epsilon j. So these are known as surface resistances, which arises because of the fact that now my emissivity is basically not equal to 1. Okay, so then this node will now correspondingly be equal to evj, and then these are the extra distances that basically come into the picture. So for real surfaces, if someone want to evaluate the qij, we'll call it as for real surface, it will basically be, so the numerator will still be equal to the difference between the emissive power nodes. And now instead of just having, the space resistance, we'll have the space resistance plus, these extra surface resistances, which will make the total resistance as 1 minus epsilon I by ai epsilon I plus 1 by ai fij plus 1 minus epsilon j by aj epsilon j. Okay, so this happens to be the net radiation exchange between the I and the J bodies had. So considering the fact that both of these are, real surfaces. So this is typically the uh, net radiation exchange for a real surface, while this Qij is the net radiation exchange for a black body now, okay, which we'll call it as Qijb. Okay, so typically you can understand that since these two quantities are there, and you can eventually show that, so if you expand these two quantities, for instance, like so I'll call these as the RTH for a real, so it's a resistance for a real surface, which we'll call RTH real. So you can see that RTH real is basically 1 minus epsilon I by ai epsilon I plus 1 by ai fij plus 1 minus epsilon 2 by aj epsilon j. Sorry, this is epsilon j. So if you kind of just rearrange, this term will basically be equal to 1 by ai epsilon I minus of what, 1 by ai, okay, plus 1 by aj epsilon j minus 1 by aj, okay. And then this term you can write it as, so for instance this term is nothing but the resistance for a black body, so you can interpret this to be equal to RTH of black. Okay, so you can now see that RTH for real, which is this, is equal to a positive quantity, because all of these are positive, plus RTH of black basically, which means that the radiation exchange between real surface is going to be anyway lesser than the radiation exchange between the surface I and J, had I and J be basically black bodies. Okay, so that is something that you can infer from the resistance network here. Okay, so nevertheless, this is nothing but the resistance network had I and J be real bodies, and this is the resistance network uh, if they were black bodies at same temperatures Ti and Tj. That is something that you need to understand. Okay, so I guess this is clear. So the important thing is, when you are comparing these resistances, basically you need to consider the fact that both I and J's are at individual temperatures Ti and Tj for you to make a valid comparison between the two. Okay. So I I hope you understand that these epsilon ij's, although I didn't explicitly mention, by now at least you should be clear that these epsilon I and epsilon j's, these are emissivities of I and J surfaces. Okay. All right. So with this, we can appreciate certain things. First of all, we have now developed a very powerful tool where we don't need to understand much about other things going on, but if we know the individual temperatures of the body of the two bodies, and if you know the certain view factors that are present, we and of course the area and the individual emissivities, if they are non-black bodies, then effectively that is sufficient to give us the net radiation exchange between the two bodies. Okay, instead of going into other ways of like calculating the fluxes and then calculating the other things, this I feel is a much more uh, standard way and a much more organized way of calculating the radiation exchange taking place between bodies, which we call it as the radiation network analysis in this particular context. Okay, so in order to appreciate this method of calculating net radiation transfer using radiation network, what we'll do is we'll now look into certain examples from which we'll try to figure out what the radiation network for the different cases would arise. And the first case that we will now see is that we will try to draw the radiation network, because ultimately we have now you know demonstrated that the net radiation exchange is nothing but the difference between the emissive power nodes divided by the net resistance. So typically, it's ultimately boils down to calculating the resistance network, which will then give you the net radiation exchange between the two bodies. Okay. So as such, we'll first look into this case where we will try to figure out how the radiation network could be. This is a very simplified scenario where we now have two infinitely long plates, and we are considering the emissivities of these two plates as epsilon 1 and epsilon 2, which are not equal to 1, meaning that these are real surfaces having areas A1 and A2 with temperatures T1 and T2 respectively. And our task, as you can see from your screen, is to draw the radiation network for this case. But just try to understand that these two plates are now infinitely long, meaning that they will extend to plus infinity and minus infinity along this particular direction. Okay. So in that context, let's try to, draw the radiation network. So as we say, always try to draw the radiation network from the emissive from the radiosity nodes, taking into account of the space resistances, and then extend it from the radiosity nodes to the emissive power nodes if the surfaces are non-black surfaces. Okay, so what we'll do is we will identify the radiosity node of surface 1, which will be equal to J1, and then the space resistance that associates between surface 1 and surface 2, which for this scenario, since there are only two surfaces, it will simply be equal to 1 upon A1 F12, or somebody can write it as 1 upon A2 F21, because the reciprocity relation holds good here. Okay, so this would be now the radiosity node of J2. Now, this would have been the radiation network. I hope you can understand that if 1 and 2 are black surfaces, but since their emissivities are not equal to 1, meaning that they are not black surfaces, we will encounter two more resistances as we saw, which is going to be the surface resistance associated with body 1 and the surface resistance associated with body 2, and that's what we'll extend it from the radiosity nodes. And typically this is the I would say the path that you need to follow whenever you are trying to draw any resistance network uh, in accordance with radiation and in radiation analysis. Okay, so this is going to be then EB2, and this is going to be EB1, and the associated surface resistance for body 1 is going to be 1 minus epsilon 1 by A1 epsilon 1, and the associated resistance for surface 2 is going to be 1 minus epsilon 2 by A2 epsilon 2. Okay, now we can now use an information that had been given to us that these two plates are infinitely long, which means that whatever the radiation that will leave surface 2, let's say, will eventually strike surface 1, which means if I say write down the summation rule for the view factors, And say I write this for surface 1, and you can eventually, you can also do it for surface 2. Say I write it for, say, for surface or plate 1. I can then say that my F11 plus F12 is going to be equal to 1. But F11 is going to be 0 because this is a flat surface, which means no way the radiation that leaves surface 1 can strike back surface 1, which means that my F12 is going to be equal to 1. And if you do the same thing for surface 2, you will simply end up, getting F22 plus F1 to be equal to 1. And similarly, the same analogy goes for surface 2, that no radiation which leaves surface 2 can strike back surface 2, meaning that F21 is also equal to 1. So whichever form you write, you will anyway see that F12 is going to be equal to F21, and also you can infer this from the symmetry of the figure as well. Okay, so nevertheless, if someone asks you now to calculate the net radiation exchange between 1 and 2, let's say we are considering the fact that T1 is greater than T2, meaning that the net radiation exchange will be taking from 1 such that 1 will try now to equilibrate, which will basically be equal to Q12. And then this radiation net radiation exchange will eventually be equal to, EB1 minus EB2, which is nothing but, the difference between the extreme emissive power nodes divided by the sum of all the resistances, which is nothing but 1 by 1 minus epsilon 1 by A1 epsilon 1 plus 1 by A1 F12 plus 1 minus epsilon 2 by A2 epsilon 2. Okay. I hope you are with me with this so far. So this is easy peasy. So that's the reason why I'm moving a little bit fast, because there is nothing much to understand here. Although there is the principle of, drawing the radiation network and analyzing the resistance, but I believe this is much of a standard way of approaching the problem. So things are a little bit easy. With respect to the other concept of radiation. This is something that I feel personally, but anyways. So, so what we saw that this F12 is basically equal to 1. And also we know that since these are infinite plates of, let's say, width V, I can then say that A1 is basically equal to A2, which is equal to A. And if I incorporate all these things into this expression, I can then say that this is equal to EB1 minus EB2 divided by 1 minus epsilon 1 by A times epsilon 1, because of the fact that, the areas are just equal to A. Since the plates are, as I said, the plates are infinitely long. So you can say that the area is basically equal to the length times the width. Length is basically going to be the same for the two plate. Width also is assumed to be the same here. Okay, so this is going to be A, and then we know that 1 by F12 is just going to be 1, so this becomes 1 by A plus 1 minus epsilon 2 by A times epsilon 2. Okay, and just we need to do some simplification. So this A can be brought to the, so 1 by A is, so it's common everywhere. 1 by 1 upon A is basically in the denominator of all the resistances, which means I can take this 1 by A common, meaning that I can bring this over here. So this is going to be the Q12 by A is sigma times of, so EB1 is going to be sigma times of T1 raised to the power 4 minus T2 raised to the power 4, which is nothing but the individual emissive power of bodies 1 and 2. And then I'll have maybe 1 by epsilon 1 minus 1 plus 1 plus 1 by epsilon 2 minus 1 maybe. Just check the algebra again. So if I'm just breaking this, which will be just 1 by epsilon 1 minus 1, and then this is just going to give me 1, and this is going to give me 1 by epsilon 2 minus 1. Yeah, I think this is correct. So then these two will cancel and we will get a nice expression which will give us the net radiative flux leaving to, you know, infinitely large plates which are at temperatures T1 and T2 possessing emissivities E1, epsilon 1 and epsilon 2, and you will get it as sigma times of T1 raised to the power 4 minus T2 raised to the power 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. That's it. So this is a nice little expression that we got, which you can see now that the net radiation exchange between the surface is a function of the individual temperature. Of course, sigma is a constant, which is just 5.67 into 10 to the power minus 8. And they are also a function of the individual emissivities. Okay. All right. So, and you can make a quick assessment out of here that if my body is 1 and 2, so these are for the case when, you know, the bodies or the plates, whatever you say, the bodies 1 and 2 are real surfaces. So what you can now do is you can draw a special case when epsilon 1 is going to be equal to epsilon 2 and this is going to be equal to 1 if you assume now that 1 and 2 are black bodies, and then you will, and if you simplify this, I mean substitute these values of epsilon 1 and epsilon 2 to be equal to 1, then you will see that q12 is just going to be equal to sigma times of t1 raised to the power 4 minus t2 raised to the power 4 by 2 minus 1, because of the fact that now these quantities are just equal to 1. Okay, which means you can now see that your expression is just going to be q12 by the area is just going to be sigma times of t1 raised to the power 4 minus t2 raised to the power 4, which again is nothing but, you know, the Stephen Boltzmann's law applied to the fact that there is a net heat transfer taking place between the two bodies, provided their temperatures are T1 and T4, and of course the fact that the view factors of the one with respect to the other, that is f12 or f21, that they are basically equal to 1. Again, this is obvious because the plates are infinitely large and they are flat, which means that their individual view factors, that is f11 and f22 is going to be equal to 0, because of the fact that for a flat surface, no amount of radiation which is leaving its surface can strike back its surface itself, which will then give you the fact that f12 is equal to f21 and this is going to be equal to 1. Okay. In that context, this gives you the net radiation exchange between the two bodies had the surfaces been black surfaces, and while this this expression gives you the net radiation exchange for the surfaces when they are non-black surfaces possessing emissivities epsilon 1 and epsilon 2 less than 1 typically. Okay, so I guess you are, so this is for the black, so this is the net radiation exchange for the case when they are black surfaces, and you know this is for the real surface. Anyway, so I believe you can now appreciate the power of, you know, the radiation network that we have used in order to calculate the net radiation exchange, because now, as I said, you don't need to really bother about, you know, the fluxes coming in, the fluxes going out and things like that. So just by knowing, you know, the emissive power nodes, the emissivities, that if their individual temperatures and the view factors, of course, you can precisely calculate what is the radiation exchange taking place between the two bodies. Of course, you need to understand the fact that the bodies are now diffuse and gray, meaning that, you know, the properties are not a function of wavelength and direction. Okay, so this, of course, this assumption is always incorrect, because now, you know, the properties, for instance, these emissivities that we have said, this is nothing but the total hemispherical emissivity that I have said, since I mean, assuming that the bodies are diffuse and gray, meaning that, the spectral and the directional effects are neglected in this scenario. Okay, so I'll maybe stop here for a couple of minutes so that you can understand and go through whatever we have done so far. And thereafter, we'll be looking into a little bit of a complicated scenario, not complicated, little bit of an involved scenario, which is known as the this infinitely long plate. This is known as the two-zone enclosure problem. Typically, because the space is enclosed between two large plates, that's sometimes that's why they are called as the two-zone enclosure problem. Now what we'll do is we'll look into a three-zone enclosure problem and try to draw the radiation network where these enclosures, as you can see now. So now instead of having two plates, you have basically three plates and possessing three different temperatures with three different emissivity values and three different areas. As again I say, the task is now to draw the radiation network for this scenario. So maybe you can think about this. Remember what I said, start from the radiosity nodes of the individual surfaces, if they are real surfaces, and then try to figure out what the space resistance will be. And after figuring out the self resistance, you can extend the radiosity nodes to the emissive power nodes by providing one surface resistance each between the radiosity node and the emissive power node. So that's the overall what to say methodology. I mean, it's not a hard and a fast rule that you always need to uh, follow that, but it's a convenient way of drawing the resistance network. So try with that. I'll anyway show it, but maybe I'll stop for a couple of minutes for you to give it a try, and I'll be happy like if you try this out your own, how to basically draw the radiation network in this three zone enclosure problem. Okay, so let's give it a try. So our objective, as I said, is to draw the radiation network for these three surfaces now. The different properties and the areas are shown. So let's then try. So what I said is always try to, draw the radiation network from the radiosity nodes. So let's pick the radiosity node of, let's say this particular surface. So that will be, that will be what? So that will be, J1 to be precise. And now let's see what are the different possible combinations of space resistance that can arise from these radiosity nodes. So J1 can have a space resistance with surface 2, and J1 can also have a space resistance with surface 3. So the space resistance uh, that is associated with surface with J1 and surface 2, so that precisely will be the radiosity node for surface 2, and this space resistance is just going to be 1 by a1 f12. Okay, that's something that we saw. Now J1 and J3 can also, have a surface resistance. Typically, this node will now be equal to J3, and this is going to be equal to 1 by A1 F13. Okay, I hope you are with me with this so far. So what we did is, as if I repeat, we picked any of these surfaces. For instance, I picked this surface 1, and then, I say that the space resistance that can arise from this surface 1, it can be with surface 2, and then it can be with surface 3. For instance, if I pick surface 2, the space resistance that can arise between surface 1 and 2 is 1 by A1 times F12. And so is what the space resistance that can arise between 1 and 3. But remember, there is also a second surface. If I pick any of the corresponding other two surfaces, okay, so then this means there can also be a space resistance between surface 2 and 3, which will be so that's why there will be one more resistance, and then this is going to be 1 by A2 F23. Okay, now you can, so what I did is we started from here. What you can do is you can start from any of the other two nodes. You will basically get the first nodes. You will basically get the first node as something like this, and there will always be another surface which will give you, which will complete basically the other space resistance when viewed from the first surface basically. You can try the same network starting from surface 3 or surface 2. You will eventually end up getting the same, you know resistance network. But remember, this would be the scenario when 1, 2, and 3 were black surfaces. But remember, now they are non-black. So what we need to do is we now need to attach the space resistances associated with these three surfaces. For instance, the space resistance that will be associated with surface 1, so we'll draw it from the node J1. So this is going to be, so the ultimate node, as you know, is going to be the EB1, that is the emissive power node. And then this is going to be J1. And now the extra resistance that will come here is nothing but the surface resistance associated with the surface 1. And we know this is going to be 1 minus epsilon 1 by A1 epsilon 1, which is, as I said, is nothing but, the surface resistance of S1, which is the surface 1. Similarly, because of the fact that the other two surfaces are also, non-black surfaces, we will then have two other surface resistance. So maybe I can draw it in a better way. Okay, and then this is going to be 1 minus epsilon 3 by A3 epsilon 3, which is again the surface resistance of S3. And then again, this is going to be the surface resistance for S2, which is going to be 1 minus epsilon 2 by A2 epsilon 2, which is going to be, the surface resistance for surface 2. And then these nodes are respectively going to be the emissive power nodes for the two surfaces, which is going to be EB2 and EB3. Okay, so as you can see from your screen, this completes the radiation network of a three-zone enclosure, and this is a very famous radiation network. So, oops, maybe I can. Okay, so I believe you can see on your screen. So this is typically the radiation network of a three-zone enclosure, and this is what the full radiation network look like. So this is nothing but radiation network of a three-zone enclosure. Oops. Okay, where the surfaces are non-black, and As I repeat, you can equivalently draw the radiation network for black surfaces. So I believe now you can understand that for black surfaces, we'll only have this part of the radiation network where you can say that J1 is basically going to be EV1, J2 is going to be equal to EV2, and J3 is going to be equal to EV3 for black surfaces. That's obvious, right? Because the surface resistance is going to be 1 minus epsilon I by AI epsilon I for I equal to 1 to 3. And for the fact that these are black surfaces, epsilon I is going to be 1, which means that this will just come out to be equal to 0. So the associated surface resistance for a black surface is 0 uh, because of the fact that their emissivities are just equal to 1. Okay, and then as I said, you'll only have this part of the radiation network coming into the picture. Okay, so now I believe at least you are in a good point where you can draw radiation network for any surfaces. And going forward, what our next objective is going to be is we'll now try to solve a practical radiation problem, because these are the case where we have just draw the radiation network and just element just in an elementary form just look what will be the net radiation exchange. But in the next example that I will show you, you will see that. You can indeed apply the concept of radiation network in actually solving a realistic problem involving radiation, which we will see which we will solve very shortly. But before that, as I said, we'll stop here. As we always do, we'll stop here for a couple of minutes. I will let you guys to recap whatever we have done so far, that is like starting from how did we you know devised the radiation network for real surfaces and for black bodies, and then subsequently looked into how to basically come up with the radiation network for a 2-zone and a 3-zone enclosure. Okay. By the way, this is known as 2-zone enclosure problem. As I'll write it here, this is also sometimes known as 2-zone enclosure problem. Okay, so before proceeding into the next problem, maybe I'll put forward the problem on your screen. You can anyway have a look. But this is a practical and a realistic problem where we'll try to actually find out the radiation exchange that is taking place to a body, which is known as the absorber surface in this scenario. And precisely, we will use the radiation network to actually solve this problem. And you will appreciate that using the radiation network actually helps into solving this kind of problems involving radiation. Okay. So maybe I'll stop here for a couple of minutes. I will come in 1 or 2 minutes by filling my mug with some water, and then we will start off solving this problem. All right, so sorry for the interruption. Let's get back to what we are doing. So let's first try to, very slowly understand this problem, what the problem is actually asking us to solve for, and then we will, formally begin the solution for this problem. Uh, Keeping in mind that now we will be using the radiation network analysis to actually get to the final answer. Okay, so as you can see, it says that in manufacturing, the special coating on a curved solar absorber surface of area A2 equal to 15 meter square is cured by exposing it to an infrared heater of width W equal to 1 meter. Okay, so there is an absorber on which there is a special kind of coating that is present on its surface. And in order to cure this coating, you are basically exposing this to a heater whose dimensions are given. The absorber and the heater are of length L equal to 10 meter, meaning that this particular length of the absorber and the length of the heater, this is equal to 10. Okay, the upper surface of the absorber and the lower surface of the heater are insulated, meaning that there cannot be radiation exchange taking place from these surfaces, which I have shown by red. Uh, which means that the only way the heat transfer that can take place by radiation is from the lower surface of the absorber and the upper surface of the heater precisely. Okay, the heater is at temperature T1 equal to 1000 Kelvin. That obviously is the case because you are providing heat to cure the surface of the absorber, and it has an emissivity of 0.9, which is of course close to a black body, while the absorber is at temperature T2, which is at 600, and has an emissivity of epsilon 2, which is equal to 0.5. The system is in a large room whose walls are at 300 Kelvin, which is the net rate of heat. So this is given. So the third object, so I hope you can realize that there obviously will be, sorry. So I hope you can realize that there obviously is going to be radiation exchange taking place between the absorber and the heater. However, there is also the surrounding where this absorber and heater, you know, is kept precisely. And the surrounding is also going to, interpret in this exchange of radiation taking place also, which means that there is also going to be radiation exchange taking place between the heater and the surrounding. And there is also going to be, exchange taking place between the absorber and the surrounding, which means you cannot just, consider the absorber and the heater alone to calculate the net radiation exchange. Because the surrounding is going to play a role into the net uh, heat transfer that is going to take place to the absorber, which we are supposed to calculate in this problem. Okay. So what we'll do is at least now we know that we need to calculate the net heat transfer taking place to the absorber, because practically that is what we seek to calculate, because we are trying to cure the bond on the absorber surface by using the heater, of course. And at the same time, what we'll try to do is we'll try to use the radiation network uh, that we have developed into, solving this problem. Nevertheless, there are multiple ways through which you can actually get to the answer of this problem, but we will stick to using the radiation network analysis. Okay. To this end, you can then realize that this is going to be a three body problem. Uh, at least because of the fact that there is a heater and an absorber, and also there is a surrounding which we will consider as the third body. And given the fact that there is no radiation losses taking place from this upper surface of the absorber and the lower surface of the heater, this means that this is going to be precisely a three body enclosure problem that we'll be dealing with, which we have kind of discussed in this particular example. Okay. But this will be somewhat of a simplified scenario, because the third body, which we'll consider as the surrounding, we are going to, assume that the surrounding is going to be so the surrounding is going to behave like a black body, which means that the radiosity and the emissive power of the surrounding is going to be the same, or in other words, that there is not going to be any surface resistances that is associated with the surrounding. So the surrounding is typically kind of a black body that we will assume, which means it will kind of simplify the tree zone enclosure radiation network that we just now, some that we drew some time ago, uh, when we kind of apply that particular radiation network into this problem. But nevertheless, let's start off this problem by actually writing the assumptions on which we can actually apply, based on which we can actually apply the radiation network analysis. But remember, so there's something that is also given. It has been said that the view factor associated with the absorber and the heater, or the heater and the absorber, F12 precisely, that is the fraction of radiation leaving the heater that strikes the absorber, is given to be equal to 0.39. Okay, this is given to you, that is given from the problem. Based on this, we will precisely try to calculate what is Q12. That's exactly the quantity of interest that I hope you can realize that we are asked to evaluate. Okay, so I will just note down certain important parameters. That is the temperature of the heater, which is given as by the index 1 is 1000 Kelvin. The emissivity of the heater is given to be equal to 0.9. Okay, and so this is the heater, and with regards to the absorber, we know that its temperature is equal to 600 Kelvin, and its emissivity is going to be equal to 0.5, and this is for the absorber. Okay, which means that the third body that we'll consider is going to be my surrounding, and we'll call this tree as the surrounding, which is my third body. Okay, with this, let's actually start to solve this problem. So we have got some hint actually, or we have got some trail of actually how to approach this problem. First of all, as I said, we can approach this using radiation network of a three zone enclosure, where one of the plates or the bodies is going to be a black body and the two others are just real surfaces. Okay, and we know that the one which is going to be the black body is the surrounding, and the real surfaces are the heater and the absorber precisely. Okay, so let's start by writing the assumptions. So first of all, we'll assume that this is a steady state scenario. Also, it's a trivial thing, but let's write it for the sake of completeness. So it's a steady state scenario that we are dealing with. The second thing is that the only way in which heat is transferred from the heater to the absorber and vice versa, and also with the surrounding, is going to be by radiation, which means that there is no convection taking place. So no convection effects. And then this is an important assumption that we'll consider, that the absorber and the heater surfaces are diffuse and gray, meaning that there is no spectral and directional effects that will come into the picture, and which also means that the spectral you know quantities are equivalent to the hemispherical total quantities of interest. Okay, and then we'll also assume one more or maybe two more assumption, which is the fact that we are considering uniform irradiation and radiosity from all surfaces. And last but not the least, the most important assumption is that we are considering the surrounding. So the surrounding room behave like a black body. Okay, so these are the assumptions that we'll consider, and of course, you need to consider this assumption in order to, use the radiation network analogy that we are trying to kind of develop here. Okay, Eh, maybe I'll stop here again for a couple of minutes. You can at least try to understand this assumption and the implication of the assumption into solving this particular problem. Okay, so so based on the assumption, as I said, that we can now view the system as a three zone enclosure with, as I said, the third surface being the surrounding, which is a black body, which is actually, so maybe I should write, which is assumed to be a black body. Okay, which means that maybe if I can draw the schematic, so I'll have the absorber, something like this. This is surface 2 of the absorber. I have my heater, which is kind of like this. Okay, and I have the surrounding that is enclosing the absorber and the heater. Uh, Maybe I'll call it as 3 because the heater is denoted as 1. So this shapes, as you can see, to be a 3-zone enclosure problem, because this is how the radiations are going to be like changed from the heater and the absorber, the heater and the surrounding and the absorber, and vice versa. Okay, so maybe I will also mention the properties here. uh, so this surface 2, which is the absorber, its emissivity and areas and temperature epsilon 2, A2 and T2. Surrounding has got an emissivity of 1 because it's a black body. Maybe its temperature is equal to T3. We will not require the area of the surrounding. Uh, Maybe you can write it as A3, but we will not require the exact magnitude of A3 in this problem. But I'll just write it. And for the heater, we know that its emissivity is given as 0.1, temperature as T1, and area as A2. Now it is given that the lengths of the heater and the absorber is given, which means that, so the length is basically going to be in a direction, perpendicular to the plane that we are drawing. So this length, as you can see, this is given as L, and this is equal to, I think they're given this length to be equal to 10. Okay, that's what they have said. Yeah, it's given to be equal to 10. Okay, so this L is given to be equal to 10, that we'll write. And the height or the distance between the absorber and the heater, this is given as H. Sorry, I think, okay, so the length is equal to 10 meter. The height, okay, so the height is given as H. That is the distance between the absorber and the heater. Maybe we'll call it as H, and that's given as H, which is equal to 1 meter. And this is precisely the length. And the width of the heater, which is given by W, this is also given to be equal to 1 meter. Okay, so what we know is, we know the area of uh, the heater, uh, the length of these heater and the absorber, and the distance of separation between the heater and the absorber, to be precise. Okay, let's you know let's let's draw this up to this point, and we will see if something else is required or not. And to this end, Now let's kind of draw the radiation network that is for a three body enclosure. So we'll now draw the radiation network. So the radiation network will look something like this. So as I said, we will start off from, the radiosity nodes of any of the surfaces. So maybe we'll start off from, the surrounding. So the surrounding radiosity node is going to be J3, but we know that the surrounding is a black body, which implies that J3 is going to be equal to EB3, meaning that there is no associated surface resistances associated with the surrounding. And then from here, I'll draw the different, space resistances. For instance, this is going to be, let's say, J1, which is the radiosity node of the heater. So the associated surface resistance is going to be 1 by A1 F13 or 1 by A3 F31. Anyways, you can do, but it's always better to write the areas in terms of either the absorber and the heater, because we don't know precisely the area of the surrounding. So we'll always write it in terms of either A1 F13 or A2 F23. Okay. So the associated space resistance between the surrounding and the absorber is going to be 1 by A2 F23. Okay. And also there is going to be a space resistance between the heater and the absorber itself, which is going to be 1 by A1 F12. Okay. All right, now this is not completed yet, because we know that the heater and the absorber are real surfaces, which means they are going to have two more extra surface resistance. The surface resistance of the absorber is going to be 1 minus epsilon 2 by A2 epsilon 2, and the surface resistance of the heater is going to be 1 minus epsilon 1 by A1 epsilon 1. Which means this node is now going to be EB2, that is the emissive power node of the absorber, and this is going to be EB1, the emissive power node of the heater. So this is what the radiation network precisely look uh, for the three zone enclosure problem. So this is the radiation network. Okay, and remember, uh, I hope you realize that the objective is to calculate the net radiation exchange between the heater and the absorber, which is just Q2. Basically, that's what we are going to calculate. In fact, it is just Q12. There is nothing known as Q2. It's going to be the exchange that we are going to calculate between the heater and the absorber, which is precisely going to be Q12. That's the objective that we'll try to calculate. So I'll write it down. So we are supposed to calculate the quantity Q12. Okay, for which I believe you now realize that we need to calculate the radiosities J1 and J2, because uh, if we know the radiosities J1 and J2, for instance, Q12 is just going to be EB1 minus J1 by 1 minus epsilon 1 by A1 epsilon 1. That is going to be Q1. Okay, that is the net radiation exchange taking place between the absorber and the heater. Or I think they're asking the net. So let's see what they're asking. They're asking the net rate of heat transfer to the absorber surface. So precisely they're actually asking us. So I'm sorry, I just forgot. So precisely they're asking us to actually calculate Q2. Okay, because they're asking the net radiation exchange taking place to the absorber surface, which means they're asking us to calculate Q2. So this is going to be Q21 precisely, which means this is going to be just EB2 minus J2 divided by 1 minus epsilon 2 by A2 epsilon 2. Okay, for which we require this quantity J2. Okay, that's the idea. Okay, so now we will see how do we basically then calculate this quantity J2, which in turn will give us Q12 from this radiation network. Okay, for which we will use a very important, law that we use in resistance circuits in electricity, and this is equally applicable for heat transfer problems as well, which is known as nothing but the Kirchhoff's junction law. And we will precisely be using this Kirchhoff's junction law into actually calculating these radiosity nodes, J2 and J1. Because you will see that J1, the equations for J1 and J2 are actually coupled, which means you need to calculate, you basically need to solve them simultaneously to actually, calculate this node, radiosity node J2. Okay, maybe I'll again stop here for a couple of minutes. You can understand how this radiation network came and the objective moving on from here that we seek to calculate. Okay, so I hope you are with me on this so far. So I hope the radiation network, at least drawing the radiation network is clear. And now what we'll do is we'll precisely, try to write equations from which we can calculate these radiosities J1 and J2, which in turn will give us Q12, that is the net heat transfer taking place to the absorber. Okay, so for this, what we'll do is we'll apply something which is known as the Kirchhoff junction law, which says that the net current coming into a junction is equal to the net current leaving the junction. It is very simple and it is straightforward to that. Now that now in terms of current, it comes into electrical circuits. Now what we'll say here is that the net flux coming into this branch is going to be the net flux, net radiation flux that will leave this branch. And if you calculate the net flux, so basically what we'll do is we'll apply, so this is known as the junction law. So we'll apply junction law at two nodes, that is at J1 and J2. So we'll apply junction law at J1. So applying junction law at J1 says that the net flux that is coming into this branch is equal to the net flux that goes out from these two branches. So the net flux that comes from this branch is going to be EV1 minus J1 divided by 1 minus epsilon 1 by A1 epsilon 1. Okay, that is typically because the heater is at the highest temperature. Okay, which means that the flux is always going to be from EB1 to the other branches, and that's the reason why the direction of this is in this particular direction and not the other way around. So this is the flux that is coming in J1, that is coming to the junction 1 at J1, and then it is equal to the flux that leaves this junction. So the flux that leaves this junction is of two types. One is J1 minus J2 divided by 1 by A1 F12. That is going to be the one of the fluxes that leaves point 1, which is J1 minus J2 divided by 1 by A1 F12, and the other one is going to be J1 minus EB3 divided by 1 by A1 F13. Okay, I hope you are basically with me so far. So just a small correction, it's not actually the flux, it's the rate of heat. So since there is an area that is involved, it is basically the rate, radiation rate that we are actually trying to see. So amount of heat that is coming into this junction 1 is what I should say is equal to the amount of heat that is leaving from junction from through this branch and through basically this branch. Precisely, it is nothing but the Kirchhoff's junction law. It is analogous to the Kirchhoff junction law that people use in electric circuits, which say that the current coming through here is I1 is equal to I3 plus I2. That's what they say. And current is again nothing but the difference between the voltage divided by the resistance, and that's what we have written here, that it is different. It is just the difference between the emissive power and the radiosity nodes divided by the associated resistance that come within these nodes. Okay. Now similarly, if one applies the junction law at J2, so if we apply the junction law at J2, we can then say that this is going to be similarly, this is going to be EB2 minus J2 divided by 1 minus epsilon 2 by 8 epsilon 2. Okay, and then this is going to be J2 minus J1 by 1 by A1 F12. Okay, or you can write A2 F21, that is up to you, plus J2 minus sigma times of T. So basically this is going to be J2 minus EB3, okay, by 1 by A2 F23. Okay, so I hope you can see that maybe I'll call this as equation 1 and maybe I'll call this as equation 2. So I hope you can appreciate that the two unknowns at least that we have apart from the view factor is that J is going to be J1 and J2. Okay, and precisely we need this J2, but you can see that J1 and J2 equations are coupled, which means we have a J1 here as well and we have a J2 here as well, which means equation 1 and 2 needs to be solved simultaneously to actually get J2. Again, this is an algebraic equation as you can see, but the main challenge that one can see here is evaluating the unknown view factors, for instance F12 and F23, because F13 is given to you. F13 is given to be what? It's given, sorry, F12 is given to be 0.39. Okay, this is given to be equal to 0.39. We require to find F13 and we also require to find F23 precisely. Okay, so this is another challenge that we need to mitigate in order to calculate these J1s and J2s, which is nothing but evaluating the unknown view vectors. Okay, so our next task is going to be, first of all, to evaluate the unknown view factors which are nothing but F13 and F23. F12, as I say, is known because this has already been given in the problem. Okay, all right. Because if we know this view factor, then this just boils down to an algebraic equation involving J1 and J2, because EB1 is known. This is just sigma times of T1 raised to the power 4 and the individual temperatures are just known. Okay, and similarly EB2 is just going to be sigma times of T2 raised to the power 4. EB3 in the same way is going to be sigma times of T3 raised to the power 4, where the temperatures T1, T2 and T3 are known to us. Okay, so I hope you understood how did we write this particular form of the junction law at the two junctions J1 and J2, and from the network that we just now drew, as you can see on your screen. Okay, so as I say, now the task that lies ahead in front of us is to evaluate the unknown view factors F13 and F23. And let's start from the fact, let's start from where we know basically. So let's do this. Let's apply the summation law. So as I said, the objective now is to calculate the view factors F13 and F23, and let's start from the summation law, summation rule applied at the heater. The reason why I said we are applying at the heater, because at least we know the view factor F12 precisely. Okay, so if I apply the summation law, it just becomes the fact that F11 plus F12 plus F13, this is going to be equal to 1. out of which you can now say that since the heater is a flat surface, this means that F11 is going to be equal to 0. This we have seen multiple times, because we know that for a flat surface, no radiation which leaves the surface can strike back the surface itself, which means that my F13, at least one of the unknown view factor, is going to be 1 minus 1 by F12, and we know our F12 is equal to 0.39, which means this is going to be 1 minus 0.39, and this is going to give you 0.61, which means at least now we know one of the unknown view factors, F13, is going to be equal to 0.61. Okay, but how do we then calculate F23? So our next task is calculation of F23, and this is where we need to be little bit wise into calculating F2. So what is F23? First of all, F23 is fraction of radiation that is leaving the absorber, which strikes the surrounding, because our tree is basically the surrounding. Okay, I hope you are aware of this. So my one is the heater, my two is the absorber, and my tree, which is basically this and this, is nothing but the surrounding. Okay, so we are basically going to calculate what is this quantity F23. So there are a couple of things that we don't know. First of all, we don't know typically the area of the surrounding. So had we know the area of the surrounding, we can use the fact that A2 F23 is basically going to be A3 F32, but we also don't know what is F32. Okay, so which means that we cannot use the view factor reciprocity rule here. The second thing, we don't know what is F22. The reason why we don't know F22 is because since this is a curved surface, now we cannot say that the fraction of radiation leaving surface 2 will not strike surface 2 itself, because there is every possibility which says that the fraction of radiation leaving surface 2 can strike back surface 2 itself. For instance, you can consider the radiation that leaves from here, it will basically strike surface 2 only, because of the fact that it's a curved surface, which means we cannot apply summation rule now at this point, at least for this curved surface uh, 2, such that we can say that F22 plus F23 plus F21 is going to be 1, and then this is going to be 0, and then we know this to basically calculate this. No, we cannot do that. But what we will now do is, in order to calculate, so see, the first of all, the reciprocity relation failed, and the summation rule failed here, which means in order to calculate this unknown F23, as I have said here, in order to calculate this unknown F23, what we'll now do is we will consider, so this is important and please pay attention. So what we'll do is we'll consider a fixacious surface, something like this, and we'll name this surface as 2 prime, where 2 prime is not a real surface, it's a fixacious surface. But at least we know that the area of 2 prime is going to be the area of the heater itself, which is just A1, because this is symmetry, right? Because we are just drawing this surface and this is the heater precisely. Okay, so I'll write it down. So in order to calculate, so this fiasco is also why we are doing all these things is because we are interested in calculating this F23. Okay, for this what we'll do is we will consider a fixacious surface. So we'll consider a fixacious surface 2 prime such that area of 2 prime is just equal to A1, which is the area of the heater. Okay, so then what what advantage do we get? So then we can say that F2 prime 3 is basically equal to F1 prime 3. Okay, this is one of the critical step in this analysis, and you need to please pay careful attention to it. So remember, we are considering the area of the fixed we are making the fixed surface in such a way that the f13 is going to be equal to f2'3. That is, from the symmetry of the figure, you can say that the fraction of radiation leaving surface 1 that strikes surface 3 is going to be the same fraction of radiation that will leave the fixed surface 2' that will strike the surrounding. And that is from symmetry, because these edges are of the same length, which is equal to 1 meter. Okay. So from the symmetry argument, this is possible, which means since I know that f13 is 0.61, this means that my f2'3 is also going to be equal to 0.61. And this is obvious, right? Because of the symmetry of the figure that we have just now stated. Which now means that I can now apply the reciprocity relation between, so this is important. So we are applying now the reciprocity relation between the fixed shear surface, okay, and this actual surface, which is A2F23 is going to be, so this is not so I'm sorry, this is not exactly the reciprocity relation. Maybe I should not write the reciprocity relation. Maybe I should tell this in some other way. So first of all, I'll write it down. So I'm saying that A2 F23 is going to be A2 prime F2 prime 3. And by this, what I mean is that whatever the radiation, so this is important, whatever the radiation that leaves surface through that strikes surface 3 is actually coming through this surface 2 prime, and that is true, right? Because we are considering 2 prime in such a way that the amount of radiation that will leave the absorber, which will strike the surrounding, is going to pass through the fixed shear surface 2 prime. Okay, so maybe I'll write it down to this explanation. So it says that, so this is true since the radiation that leaves the actual surface which is 2, they all pass through the fixed shear surface, which is 2 prime. Okay, which now means I can then calculate the actual F23 as the area of the fixed shear surface by the area of the actual surface times F2 prime 3. And we know that the area of the fixed shear surface is going to be 10. This is going to be 15. That's given to us. And then this is 0.61. We already calculated, which means my F23, which is actually, the amount of radiation, the fraction of radiation that leaves the absorber that strikes the surrounding, is going to be equal to 0.41 if you just calculate this particular uh, multiplication. Okay, so that's it. We have now reached the actual F23 that we require to, in order to calculate, as I said, the unknowns J1 and J2 from equations 1 and equation 2. Okay, so now what you need to do is, if you substitute all the values of the view factor and the temperature and the emissivities, so I'll not show this step, so I'll just skip this particular step because this is obvious. So I hope you understand that the most important step of this problem is to identify the fixed shear surface and then use the fixed shear surface in order to calculate the actual F23 for this particular problem. Okay, so now what you need to do is you just need to substitute everything. So substitute everything, and by everything I means the temperatures, the emissivities, and the view factors in equation 1 and 2. And if you do so, I'll skip this math because I believe you are, by the end of this time of the course, I believe you are expert in these things. You will just get two simplified algebraic expression which will look something like this. So I have a priori calculated that. So this is going to be minus 10 J1 plus 0.39 J2 and this is going to be minus 510,582, and the other one is going to be 0.26 J1 minus 1.67 J2, and this is going to be minus 7536. Okay, so these are the two algebraic expressions that you need to solve, and if you solve this, what you will get is you will get J2 to be around 12487 watt per meter square. Okay, that is the radiosity, and then you can use the value of J2 to find J1, but we don't require J1 here because that is not asked in this problem. Because in the problem, what they're asking us to basically calculate the net heat transfer to the absorber. So in fact, this Q21 is just going to be, your EB2 minus J2 by 1 minus epsilon 2 by A2 epsilon 2. And if you just substitute all the values, because all these quantities are known except J2, which we just now calculated here, your Q21 is just going to be, so this is not actually Q21, this is going to be Q2 because there are multiple, interactions taking place. Maybe we should write it just by Q2 itself. And then this is going to be around minus 77.1 kilowatt, and this is the net heat transfer to the absorber. So we are not writing Q21 because there is also the surface 3. Okay, so it's better to write Q2 rather than writing just Q21. Okay, so that's it, guys. That's the net heat transfer taking place to the absorber. So as I said, this is the net heat transfer taking place at the absorber surface. Okay, that's it. So that's it, guys. So this is the solution to this problem. This is a good problem, I should say, because it involved multiple concepts. First, building the enclosure itself, which is basically this, using the surrounding to our advantage and taking use of the fact that the surrounding, I mean, assuming the fact that the surrounding is a black body, and assuming that the absorber's upper surface and the heater's lower surfaces doesn't exchange radiation, which gave us an idea to actually form the absorber and then make the radiation network, sorry, not the absorber, I mean to form the enclosure and then make use of the radiation network in order to form a kind of 3-zone enclosure. And then, applying, the second thing is then learning to how to apply the junctions law, where we are just equating the currents at the junctions to the currents coming in equal to the sum of the currents going out. And then, using these two to actually realize that we ultimately need to calculate the radiosity J2, but it is where we encountered a problem that we didn't knew the view factor, at least the view factor F23 that basically appeared here. And then what we did is we applied summation rule to get first calculate F13, and then using the help of the fictitious surface, we calculated F23 with the assumption that all the radiation that leaves the surface 2 will always pass through the fictitious surface 2 prime, from which we calculated F23, and then it was just about solving two algebraic equations involving the unknown J1 and J2, from which we calculate the net radiation transfer taking place at the absorber surface, from the fact that it is just going to be the difference between the MEC power nodes and the radiosity nodes at 2 divided by the surface resistance associated with the absorber, which gave us to be around minus 77 kilowatt, and the minus sign is obvious because the net heat transfer is taking place from the heater to the absorber. Okay, because the heater is at a is at a higher temperature than all the three bodies combined. Okay, so we will then stop here today, and this completes our understanding of the radiation network. And what we'll do in the last class, which is going to be mostly on Monday, is that we will now try to apply this radiation network into the final application, which are nothing but radiation shields, where we'll see that this analogy of using radiation network, I mean, the idea of using radiation network can be extended to understanding the radiation exchange taking place in certain bodies, which are known as radiation shields, which are typically used, in places where we are trying to minimize the heat loss due to radiation. So naturally, as we'll see and we will discuss, that these shields are typically made of low emissivity materials, because actually we're trying to minimize the heat loss that is going to take place between the actual parent materials. Okay, and we'll use the concept of radiation network into evaluating the radiation exchange taking place between radiation shields And then what we'll do is we'll do a final recapitulation of the course from the day one to the date from the week one to the week 13th, and that is where we'll end the formal discussions of this course. So that's what we will plan to do it in the last class, which will mostly be on Monday. You will a priori be informed the exact timing. So this is going to be an extra class, and you will be informed the actual timing of the extra class through emails and on the course website as well. Okay, so see you mostly on Monday. It is because yeah, I mean, I have conveyed to the NPTEL team that I wish to conduct this extra class on Monday. The exact timings will be shared to you through emails and on the course website, and also maybe through the discussion forum. It will be posted. Okay, so and I request everyone to join that class, because this is going to be that last class where we'll be discussing the doubts, and thereafter you are supposed to write the exams for this course. Okay, so as I said, on Monday the first agenda is going to be discussion on the radiation shields, and then we will do a quick recap of everything, and the floor will be open to discussions and questions for all the weeks, including the last week, which is going to be 13. Okay, so that's the idea that of on I mean what we are supposed to do on the last class. Once again, thank you all for joining and for watching these videos. Please let me know if you have any doubts associated with all these things. And if not, we will see you on Monday maybe on for the last class of this course. Okay. Thank you very much.